Okay, back to the steady state pull-up. Same procedures as turning flight. We just have different rates. Meaning P1, Q1, and R1 are not the same as for a turn. The difference here is it actually makes it easier. The pitch rate is non-zero, and that's what we had as 0 for the turning flight. P1 is 0, and R1 is 0. And even nicer, the bank angle is 0. And there's no real lateral directional anything, so the side slip is 0. We're in stability axis. So W is 0. And we're at the bottom of the loop. Which means the flight path angle and the pitch angle are 0. And we analyze it at the bottom of the loop because that's when you're pulling the most G's. When your weight is down and the centrally acting force is upward. So this makes this a lot easier. The lateral directional equations are not needed. Now that said, if we decided we wanted to analyze a one-engine inoperative pull-up, then we'd have to go back to doing the lateral directional equations along with the longitudinal. But we're just going to do a standard pull-up. If you don't have one engine working, you really shouldn't be doing much maneuvering anyway. Definitely not a pull-up. And maybe a real gentle turn. So a real quick picture of what's going on is we have a center of curvature here. This is the path that the airplane is going on the loop. That's the radius of the loop. Airplane is down here. We have weight acting downward. Notice I've drawn lift bigger than the weight. That's because the lift provides not only the weight, but the centrally acting force that causes the circular motion. So lift is greater than the weight, and we're analyzing at this bottom of the loop. Just like in regular cruise flight or turning flight, we go back to the steady state equations of motion, specialize them for this flight condition, plug in the lift, drag, and pitching moment linear steady state models, and then we go from there. So I'm going to pull those up. So back to chapter 1, the steady state equations of motion. You can see they're going to be simplified a lot because V and R are 0, W is 0. U1 and Q1 are not 0, so we're going to keep this term. V1 goes away. And then in the pitching moment equation, P and R, 0, 0, 0, 0. So the trim solution turns out to be pretty straightforward. The only wrinkle is we've got pitch rate in here that we didn't have in the cruise flight condition. We need the formulas for the FAX, FAZ, and MA. Those are our standard linear models. So we go to chapter 3, where we develop the linear models. We say that, for example, the lift is a function of angle of attack, incidence angle, elevator. And since we have a pitch rate, we're going to have to add on another term to that for the pitch rate. So we're going to assemble those next. I'm going to write those on the board. And we're going to look at the unknowns and how to solve this. So here's the drag equation. Which we already saw. And then we're going to substitute in the drag model for FAX. And then here's the thrust model. And we still have to put the gravity term in here. Normally we list it up here. I don't know. I moved it over here. Maybe it's because it goes away because theta is 0. We're at the bottom of the loop. So that's the drag equation. And we knock out V1 and R1. We're in stability axis, so W1 is 0. Then we got the lift equation. By the way, the other name for the drag equation, if we're in more general, this is the X force equation. It becomes a drag equation because in stability axis, drag is in the XS direction. And this is the Z force equation. Knock out those terms. There's the gravity term. The bank angle we said was 0, and the pitch angle is 0, so that simplifies. And then here is the pitch rate term. We use this, I guess we didn't use this in the turn because the turn had P and R, right? No, my bad, we had that in there because P is 0 in the turn, Q and R were in the turn, or non-zero. So this is an extra term because of the maneuver. There's the elevator, there's IH, so we're done with this. Got to multiply by Q bar. Yes, good, I remember to do that up here. And then here's the thrust component in the vertical direction. So these equations should look familiar because we used these exact equations for the cruise flight condition. The only thing different is that Q is 0 in addition to P and R. So those terms all got knocked out. And fundamentally, then it becomes lift equals weight in the cruise condition and thrust equals drag. But we're doing a turn, not the turn, we're doing a pull-up, a maneuvering flight, so those Q terms show up in there now. And then the pitching moment equation. This is really nice because P and R, gone. Again, this is where we're specializing it to the pull-up, is when we knock out these various rates. And then here's our standard linear model. And this brings up a joke that the comedian John Mulaney talks about. You guys ever watch him? You know how you can tell an artist from a non-artist? When a non-artist starts writing, say, their name on a piece of paper, they always run out of room off to the right. Whereas an artist visually looks at it and sees the letters on it and spaces it so it fits. I've seen it happen. My wife's an artist. She never runs out of room. I always do. And the comedian was talking about that. He said that he always runs out of room when he's doing that. So you can see this happening when I write equations. Of course, I'm trying to write them big so you can see them, so I guess I have that excuse, right? So don't feel bad if you run out of room. It means you're an engineer or a scientist and you're writing really big and important equations, and that's why you run out of room, right? Okay, so we've specialized these for the steady state pull-up condition. In the book, he says this term is important for the pull-up. But he said typically this is small, mainly because the effect here is you have an airplane, and if it has a pitch rate, the cap of the pin marker here is the tail. In a pitch rate, that tail is moving downward. And so you get some extra angle of attack on that tail. And it can definitely produce a lot of pitching moment because the tail is way back in the back. But it doesn't significantly change the lift for normal pull-ups. Now, if you're in a spin, if the airplane's spinning, that's a totally different story. But for this, for normal pull-ups, where the pilot's not blacking out from the G's and the wings aren't falling off, that you can consider that term to be small. Okay, how are we going to solve this? Pretty much like we solved all of the other steady state flight conditions. The nice thing about steady state is this is not a differential equation. It's an algebraic equation that we solve for the unknowns. Hopefully the green marker shows up well enough. I'm going to circle the unknowns. Is that showing up on the screen okay? Can you see it? Oh, that's not too bad. Put a 1 on the T down here, I forgot it. So there's our unknowns. We're going to specify IH. We're going to specify the airspeed just like we always do. We're going to say we're doing a pull-up at 150 knots. The tail is already attached to the airplane and is rigidly attached. Q is going to be determined by the load factor or the turn rate, which we'll derive here in a minute. So these are the three unknowns, and these are the three equations. So we should be able to solve this, right? So a good test question, maybe on the final or some other test, is why can't we solve these three algebraic equations for three unknowns? What's the problem? Same problem we had with cruise flight. Yeah, you're looking at the sine and cosine terms, right? We looked at those before. Here's alpha. Oh, I forgot to circle it. Let me circle that one. It's red because I lose points because I forgot to circle it. So in cruise flight, when we solved this, we said, well, let's make some approximations. Let's say that this is a small angle. So we can knock that out of the lift equation. Now, if it's a V-STOL airplane and the thrust vector is pointed down, phi sub t is like 90 degrees, you can't knock that out. But for normal airplanes and normal pull-ups, you can. So we're going to say that's small. But we really can't say this is small, can we? Cosine, so we're stuck. But the next thing we said was dt is small. We did a good job of aligning our thrust vector with the x-axis, so it pretty much counteracts drag and doesn't provide lift. Again, a VTOL airplane, that doesn't work. The thrust vector is completely the other direction, and you've got to solve this in a different way. So we throw that away, and the advantage then is that the thrust terms are gone in the bottom two equations, so we can solve for just these two unknowns, get alpha, and then put alpha right up here, and then solve the thrust equation separately, just like we did with cruise. So we get the 2x2 trim solution for alpha and elevator, just like before. And it makes it easy to solve this. Oh, here we go. So let me knock out the terms that are gone, and we need to talk about one term in particular here. In fact, I want to erase a little bit here, and then we're going to write the two equations we're going to deal with. So let's see. This is gone. Nope, I erased something that's not gone. Right? That's still there. This is 0. We've knocked that out. We've knocked that out. We've knocked this out. The top equation, we're going to separate out. This is all gone. And we're going to call all this stuff in here just the drag coefficient, whatever it might be. Let's see, this was gone, right? So the first thing we notice is that we can solve that top equation for T1 if we know alpha and elevator from the bottom two. So we're good there. So we'll just write that solve for T1. The nice thing about this is you can use this linear model, or you can use the drag polar, just like for cruise flight. So if you have an accurate drag polar, you can pop that in there and get a better solution for that. Next thing we want to do is shove the unknown terms over to the other side. So there's a minus sign here, so that's going to go over here. We're going to shove this over to the right. We're going to put the CM unknown terms on the left here. And so we're going to get a matrix that has this entry, and this entry, and this entry, and this entry. And the only thing, let's erase this out of here too. I don't want to look at it anymore. The only thing we really need to work on are these two terms here and plugging in for Q here. So let's get our matrix going. We'll write this. I want to save that there for a minute so I don't have to look back and find it. So here's our matrix problem for the bottom. So those are the terms I shoved over to that side. So we're going to work on this for a minute. I need this term here. In fact, it's in the perfect spot. Look at that, it's right there. CMQ, Q1, C bar, over 2U1, so we're good. So this is the matrix problem that we need to solve, and we need to plug in for Q. And then once we're done here, we go up here and solve for T1, so it's all good. So we're going to come back to this in a minute. I'll give you a minute to catch up because I'm going to switch over to the tablet because I want to leave this up on the board so we can come back to it. But now we need to do some physics of the circular motion of a pull-up. I was just imagining the class all sitting with virtual reality goggles on, wherever they are, and attending virtually, because we're getting a pair for my flight sim lab. And I don't know if you've seen it, but there's a movie where that happens. It's called Ready Player One. You seen that? It's about the future where everybody does virtual reality, and they live in this virtual world where they go around and play video games. It's a fun movie, look it up. The book is better, especially for that one. The Martian, which we talked about I think earlier, the Martian movie was really good and the book was good, but this one, the Ready Player One book was better. Okay, so everybody caught up here while I talked about movies? Okay, good. So we want to do this picture and do the math on it. So there's a couple things we need to add to this. We've got the lift there. the pitch rate that we've been talking about is this angular rate Q1. So if you want to redraw this figure on your notes in this point so that then the derivation we're going to do is below it. I want to knock out this because I want to write something there. So the lift counteracts the weight, but it also provides a centrally acting force that we know from physics depends on the mass and the velocity squared, and then it's inversely proportional to the radius of the loop. So that's the required force or centripetal force needed to do this. And similar to last time, we know that the velocity along the arc is the angular rate times the radius of the loop. And remember, that came from the fact that the arc length is equal to the subtended angle times the radius. And if you take the derivative of that, you get velocity and angular rate. So we're going to use that in the force balance equation. So if we look in the vertical direction, we find out that lift minus weight is providing that force. And we want to plug in for one of the U1s here. So then the R loop cancels with the R loop, and we end up with MU1 Q1. And then we're going to move the weight over to the other side to find out what the total lift is. So this is an easier force balance than the turning flight, because in turning flight we had vertical directions and horizontal directions. And here all we've got is vertical. So here lift is equal to mg plus m u1 q1. And if we look at our equation, oh, I forgot to divide through by q bar s up here. Let's help me remember to point this out. We need a q bar s because we divided through the lift equation by that. So underneath this term that shows up in the lift equation, mg mu q1, we divided by q bar s. And so this term is exactly the term that we have in the lift equation for the trim problem that we had on the board. And so in the turn, let's see if I have any extra room over here. This is just going to be load factor times CL1. Why? Because load factor is lift divided by weight And so that's what we have on the right is mass divided by Q bar S. So this extra term here is providing the extra that we need for the load factor. Right, mg over Q bar S is just CL1 so with the extra force needed to provide the centrally acting force, we get the load factor out of this. Okay, the other thing we need to do is we want to solve this equation for Q1. So Q1 is going to be lift minus mg divided by mu1. And this is N mg by definition of load factor. So the masses cancel out. And we get a nice simple expression for Q1 that we need to substitute into Q1 on the board. And so the term mg plus mu1 Q1 over Q bar S, we just plug in N CL1. And that came from this force balance equation. And then also from the force balance equation, we find out what Q1 is. So we're going to jump back to the board. As soon as you guys are caught up. And the one thing to notice is just like in the turning flight, when we did the force balances, the force balance of the physics, the terms that showed up in the equations of motion for steady state flight were determined by the force balances of the free body diagram. So in turning flight, that's how we got R1 and Q1. And here, the force balance gives us Q1 in terms of load factor, just like we did over there. All right, can I switch back to the board? Is everybody caught up with this? So if we do that, and then for those of you on Zoom that I didn't switch back, I had forgotten to divide through by that because the CL terms are multiplied by Q bar S in the equation. So just to add that, that was a mistake. And now, based on what we just did, this term is just N times CL1, where CL1 is the steady state cruise load lift. And then we plug in for Q1 here with the formula we just derived. And we get another U1 down on the bottom from that, and then the Q gets turned into the load factor representation that we had, which was G times N minus 1, because we had G N minus 1 over U1 for that. And so now this problem is in terms of load factor specifying the turn. The turn rate, the pull-up rate is Q, and we've substituted for that in terms of load factor. So that wraps up pull-up flight, except for two things. One, we need the solution to this. So again, just like the turn, you can do it two ways. You can plug numbers into the matrix and then use a matrix solver to solve for alpha and elevator. Or we can use Kramer's rule. Which are the solutions that I'm going to show you that are in the book. And just like before, we get the determinant of this thing in the denominator, and then you get a whole bunch of stuff on the top because you have to substitute in the right-hand side in for the different columns to solve it for Kramer's rule. So again, just to keep track, we're going to solve this for alpha and elevator, and then those go up into this top equation where you solve for the thrust. Kramer's rule. Pretty sure it starts with a C. I always get, in my mind, think sometimes it starts with a K. You guys know? Pretty sure it's a C. But I would not bet $1,000 on it. So the solutions are in your book. There's the matrix problem we just formulated, and he shows the solutions. Here's the solution for alpha, page 232. Notice that load factor shows up in here and in here. If you're doing cruise flight, load factor is 1, so this term drops out. Make sure that it makes sense because there's no Q. This term becomes CL trim, which is the steady state cruise CL for a rectilinear flight. So that makes sense. So you can actually plug in n equal to 1 in this or the turning equations, and you get the rectilinear flight cruise. And then the elevator solution looks like this. Again, the 2x2 solution in a matrix solver works just fine if you're plugging numbers in. But like before, we want to know, well, how does the elevator change with load factor? So we want to take the derivative of this with respect to delta E, because we want that to be negative, to pull on the stick. Same story. I can't draw over here. There's supposed to be a 0. So it has to be less than 0, which means that you pull on the stick. The elevator is positive, trailing edge down. So to pull it trailing edge up means you're adding pitch rate. Obviously, in the pull up, makes a lot of sense because you want to pitch the nose up, so you pull on the stick. And we want that to happen. And that happens when the change in elevator with respect to elevator, I need a derivative here, don't I, is negative. So the terms that get impacted are this one here and this one. This is a nice derivative because we just get derivative of n is 1 and the derivative of n is 1. So there's what the derivative looks like. It just has those two terms. Yeah, derivative with respect, well, why did I write this? Is scratch that out. Don't know what I was talking about. The derivative of elevator with respect to itself is what? Yeah, this should be n. And that's what's here. So you can see where this comes from, right? This term here goes just straight here. This term here goes straight here, and then you get the denominator. So again, CM alpha depends upon CG location. We know that. That's pitch stability. And so we can find a CG location that makes this 0, and that's the place we want to avoid. We want feedback, and we want good feedback. So that is called the pull-up maneuver point. And this is where he solves for that. And in the process he writes, I'm going to try to write on here with this rather than switching around too much. So we're going to use the formula just like before. That's an AC. So this is just our old formula, CG minus AC location times CL alpha gives CM alpha. You plug this in here, set it to 0 for the maneuver point. CL alphas cancel out, and you get a nice formula for the maneuver point. This is stick fixed because we're not saying that there's a trim tab and the elevator's floating. We are holding rigidly onto the stick. So then we ask the question, where does this located relative to the AC? Because that's what this formula is telling us. CMQ is typically, if the airplane is pitch stable, in pitch rate is a negative number. And so a negative and a negative give a positive, which means that the maneuver point is behind the aerodynamic center. And we know that we always want the CG in front of the aerodynamic center to get pitch stability. And so typically we're good with respect to this. But we have to calculate it. Can I what? Yeah.
So when you take derivative of the first n, that becomes 1, right?
Yeah.
So 1 minus 1, wouldn't that be 0? The term would go away, right?
Well, the derivative of n is 1, but the derivative of 1 is 0.
Okay, the full term.
Over here?
Yeah.
So the derivative of n with respect to n is 1. Yeah, this is multiplied by CM alpha, and this is multiplied by CL alpha, so they don't cancel out. You get this term on the top, right? Were you looking at this?
Yeah.
Yeah, so the derivative of n with respect to n is 1. The derivative of a constant with respect to n is 0.
Right.
Yeah. Next thing I want to look at is, what do we do if you can't knock out these sine and cosine terms in either the cruise condition, the pull-up condition, or the turning condition? I'm not still sharing my screen, am I? You're seeing this on the Zoom. Yeah, okay. So what are we going to do about that? We can't knock out the cosine, we can't knock out the sine term that was here. That means that we have to solve this in a non-algebraic way. When one of the ways to do that, to solve transcendental equations, is to do an iterative trim solution, meaning that we guess a value for alpha in elevator, evaluate the sine and cosine terms, get a better estimate by solving the trim problem, go back and do it again and again and again. So that's what I'm going to show you next. So for the cruise, we can knock this down, just plug in n equal to 1, and then we're back to the cruise trim problem. But we need to put in those sine and cosine terms. I've left that one in here. The lift term the lift equation has that sine term, so I need to add that in. So I've got those. All right, you guys remember that term, right? We knocked it out earlier. And so that has to be put in here. And then we might as well add in the thrust term here as well, because the only reason we knocked that out was because it allowed us to separate the equation. So let's leave that in. And you know, CT is T over Q bar S. You did that in one of the homework problems. And so we're stuck with the sines and cosines, but the iterative process now that we do this with this is, let me erase up here. So this is, we're back to the cruise. Trim flight problem that we had before. But we have these transcendental nonlinear terms, and these things are coupled because thrust is down here and thrust is up here. And so the first thing we do is we guess an initial trim solution, which means we get an alpha one, an elevator one, and a T1, and then from T1 we can calculate CT. But it's not going to be right because we're just guessing. So somebody guess a value for alpha. 5, okay, 5 radians or 5 degrees? Radians? Degrees, yeah, 5 radians, gosh, we're flying a really high angle attack. Elevator, pick a number. -2, thrust. You don't even know what the airplane is. How could you, you know, 10,000, right? So you take those numbers and you stick them in here and here and here. And then you solve for a new alpha and a new elevator. It's going to be a little bit better because we just randomly guessed at least these are going to satisfy this equation, right? And then we take alpha and elevator, the new values, and we stick it up here. And up here for the thrust, sorry, up here, and then we solve for a new thrust. So you might put new here and new here, and these are all the old values that were the guesses that started the whole thing off. This is going to be the old alpha and the old elevator. So we guess, right, old up here, because now that's what I'm calling these. We guess the old values go in wherever we can't deal with them, solve for the new values here, solve for a new thrust here, and guess what? We do it again. With the new values become the old values. So the new ones go up here and become old. And then we substitute in where we can't deal with them. We substitute in the right-hand side there and up there. We get the new values here, and we keep doing it, and we get better and better and better until alpha doesn't change by very much, and we know we're getting close and converge to a solution. Again, with this, just like anything else, you can use a drag polar or the linear drag model, depending on what you have. Now, I don't know about you, I probably do, in that you don't want to do this by hand, right? Because maybe we have to go through this process 10, 15, 20,000 times until it converges. So we're going to do this with a MATLAB code. And the MATLAB code is real similar to the one that you guys used when you calculated your trim solution and you plugged it in and you saw, well, it wasn't quite right, but it got pretty close. And in fact, that brings up the question is, can we do better than just guessing like you guys did for a trim solution? I mean, we were just pulling numbers out of the air, right? What's a better value than just guessing? How about that trim solution you did in the previous homework? So you can solve this approximate, right? The trim solution where we knock this out and knock this out, and you can get a pretty good estimate. You saw it wasn't bad. And then that's your initial guess is from the 2 by 2, and the thrust you get from that. And in fact, in the homework, you're going to do this. You're going to go for that same airplane, you're going to go back and get your solution from homework number 4. That's going to be the initial guess. And then you're going to write the short bit of code in MATLAB to do this. I have a whole file. Yeah, because I'm not asking you to reinvent the wheel, just to add this to the code. So this code looks familiar because it's based on the code where you plugged in your numbers for the trim solution. Here's where you put your solution in, and then it's called the Simulink program that gave you the plots. And in fact, that's what this is. It sets up the same parameters, sets up the same airplane. But once, right before we call the Simulink simulation, we're going to improve on that alpha thrust and elevator, and that's going to go right here. So this file is on Blackboard, and all you're going to do is add a while loop it's a crappy eye. A while loop here is that while alpha, the angle of attack changes greater than 0.00001, it's in the homework. You're just going to check the new alpha, compare it to the old alpha, and if that changes less than the specified amount, you call it good and you drop out of the loop. The advantage you guys have over like 5 years ago is you've all had MATLAB. You know how to do this. This is easy. Some students in the past had to kind of learn MATLAB from Fortran to do this, and they figured it out and they had learned it. But that's all you're going to do here is you're going to set up this matrix problem. The parameters are all specified above. So you're going to calculate the numbers to go on the right-hand side. You're going to set up the matrix, and you're going to tell MATLAB to solve that matrix problem for alpha and elevator. You're going to need those initial guesses that come from the top. And so make sure you use those just to set the right-hand side of this. And then you'll plug them in here, calculate the thrust, then you go back and do it again. And that's all done inside the while loop. The number one mistake students make, they'll get this set up right and solve the matrix, but they'll forget to do this. In other words, you just keep the same thrust of the initial guess and forget to calculate a new thrust. So in reality, this takes maybe 10 lines of code to do, if that. The key thing that you have to focus on, I've noted here, is that the initial values coming into your loop are in degrees. So those values that you type in at the top are in degrees. You need to convert them to radians because all of the parameters are in radians. You guys know how to do that. You just multiply by pi and divide by 180. And then you'll do your iterative trim solution. And when you drop out of the while loop, you need to go into a section of code that converts it back into degrees, because later on, the MATLAB simulation wants degrees. So don't worry about what's down here and what's going on. you need your values coming out in degrees, and you have to realize that coming in, they are in degrees. So degrees in, degrees out, but inside here, you need to be in radians. So you'll take this code, add your trim loop, and then you'll plug in the trim solution that you got from homework number 4. Here. And it sounds daunting, but it really isn't. Literally 10 lines of code. Make sure you get your matrix set up with the right values in there. Notice those values are in here. Here's CL0, here's CL alpha, here's CM0, here's CM alpha. Everything you need is here. Just get the matrix set up. Calculate your B vector on the right-hand side. Make sure that B vector gets updated every time you do the loop. Make sure you update your thrust every time you do your loop, and it will converge. And you will get, on a reasonable scale, if alpha is scaled from like 0 to 10, you'll get a straight line across. Alpha will trim perfectly. Airspeed will trim perfectly. Now, if you do auto scale and you zoom in and it goes from like 9.1 to 9.2 and you zoom out, you will see some oscillations. But if you keep it on a normal scale, you'll see a nice trim solution. So look at that, start working on it, and then come back. Usually there's some questions and I'll help clear that up.
How many more coding homework do we have?
How many what?
Coding homework do we have?
Total?
Yeah, what?
Like, I'd have to look, I don't remember. Usually adds up to maybe like 10 or 11.
Coding homework, where we write code.
Say that again.
Coding homework, where we write a code.
I think this is the only one.
Okay.
So my question is, what we do after we get the new thrust?
The new thrust.
Yeah, after we get the new thrust, what's the next step?
So you get a new alpha, a new elevator up here, new thrust, and then it goes in here. It becomes old. So all of the new stuff is now old news because you're going to do it again. And again, code it up. You'll get to a point where you go, what am I doing? And then ask questions. So this is due on Thursday, not this Thursday, but next Thursday. So don't wait till Wednesday to do this because you will have questions. That's why I give you a week and a half. Start on this, come back with questions next time or the Tuesday after that. And that's all I wanted to do today, so we're done.